Good morning, and hello to my amazing talk on QEMU in UEFI, in case it wasn't obvious. So who am I? I'm Alexander Graf. I'm a KVM and QEMU developer working for SUSE, and I've done things like, for example, the server class PowerPC port, or nested SVM, in case you've been running virtual machines on your AMD machine inside a virtual machine with KVM. I'm slightly at fault on that one. I was one of the founding members of the SUSE and OpenSUSE ARM teams, so I've been involved a lot with ARM things recently, and I did things like the UEFI support, which got me into the whole UEFI story in general. And this is work that just happened because I happen to know ARM and UEFI. But to figure out what the differences are, imagine you have two systems. You have an ARM system, this is ARM64, and an x86 system, this is x86-64. We're not talking 32-bit anymore. If you have these systems and you plug in a graphics card, and then you attach a monitor, and then you boot them up, what happens? Well, your x86 system just works, right? You plug in your graphics card, turn on, you can see the nice logo and everything is shiny and great, and your ARM system barks and basically doesn't make it. Because it doesn't know how to talk to that new graphics card. So, why does your x86 system know how to talk to that graphics card? Well, that was easy. The graphics card itself has a small storage space on it called Nocturne, which provides a driver for the firmware that's running on your x86 system. These days, it's usually UEFI binary. And that firmware is, or that firmware driver is an x86 binary block. So if you have, so back at the now Connect a couple, like about a year ago, roughly, give or take, Art and me sat down together because a now member started complaining about the fact that they couldn't use, they just recently acquired another company that produced network cards, and they couldn't use their own network cards in their own ARM servers. And they complained about that fact, which I can certainly understand. So we sat down together and figured out what we can do to work around that whole issue. And there have always been ways to work around limitations with optionals in the field, but nothing ever got to a place where you could actually use it. So to understand why this really is an issue, let's first take a look at what the difference really is between x86 and ARM. So if you, from a really 10,000 feet perspective, look at them and you just see, well, this is ARM, this is x86, you can see registers. Who of you knows what registers are? Okay. So registers are basically a small storage entity that you can use in your CPU to put data into, to put integers, numbers into, and then you can do operations on those fields. So if you want to do any operation like an app or anything, it has to happen on these, instead of these small buckets. And then you can combine these together, for example, with an app. So every operation happens on registers. And as you can see, x86 has vastly different register names and different number, and everything just looks different from ARM. If you, for example, want to move, you just want to copy data. You want to copy the contents of this one register into this other register. Ignore the names, but still, you just want to do the same operation. You want to copy something from one register to another. The operation to it is even called slightly differently, but down here you can see the instruction stream, the hex codes of what the CPU reads, and you can see that they look vastly different. There's basically no resemblance between one and the other. And the way to make one thing work on another thing, that's what emulators are. And QEMU is a really nice emulator that happens to actually already implement a way to run x86 instructions on your ARM CPU. Or it really actually makes anything amazing. So let's get to that point. What is QEMU? So QEMU emulates machines, usually, right? Something in your system. But what actually comprises of your system and what does system emulation mean? So in system emulation mode, QEMU starts the whole stack of everything that your computer is composed of. It emulates your CPU, it emulates your hardware, every single piece, your devices, everything you have. And because it emulates your CPUs, it also emulates every instruction running on these CPUs, which means it emulates your kernel that's running on that virtual hardware, and it emulates your user space applications that are running on that virtual hardware. And that's what we call system emulation in QEMU. That's a really slight trick to that whole thing, where you leave the CPU emulation part out and you push it into your host CPU, and that's what KVM is about. But in a traditional sense, this system emulation basically just emulates the full system, everything, hardware, top to bottom, the whole stack. Then there's something called Linux user emulation. With Linux user emulation, what you do is you basically draw the line where your app emulates something way higher up the stack. So QEMU goes and emulates the kernel to user space interface from the syscall interface. And basically it only converts the structures that are needed from one to the other, and the numbers that are needed from one to the other to be able to run a, say, PowerPC big endian guest binary on your x86 host system. So it has a lot of conversion code in there to convert the structures and to convert syscall numbers, and then just invokes the same call that was invoked by the guest binary on the host Linux kernel again. Which is much more lightweight, much faster, and actually more elegant in the way to run code. But that's not what we need, because in the firmware environment, this doesn't help us anything, because firmware is different. In firmware, we have this thing called UEFI that's just running on our hardware, and it does something. So who of you understands what UEFI really is doing? That's way more hands than I was expecting. Awesome, very good, very good. This is the right audience. So UEFI, what does UEFI do? UEFI basically drives your hardware. It's the first thing, no, not the first thing, but it's the first thing that you see that comes up on your PC. If you boot up your PC, there's small initialization code, and then there's your firmware, your actual big firmware, your UEFI core parts that go and run. And those things have drivers. They have drivers for your block device, for your network adapter, for your graphics card, for your CD-ROM, for everything you have in your system. There are drivers inside your firmware. And these drivers then connect to the UEFI core and basically talk to each other. This is like a really big bucket of random drivers that can communicate. But they cannot just communicate with each other. You can even do fancy things like use your block device to load a payload, like say Grub, to then again have Grub access that same storage backend to load another payload, like say Linux, and then execute Linux and then pass over access to the system over there into Linux itself. So this blue line means there's a special node when Linux boots up, it basically removes most of the UEFI driver parts and just leaves a small piece called runtime services allowed. This is UEFI 10-second walkthrough. So let's take a deeper look at what happens when a driver gets initialized. So if you have a driver for a, say, disk device, what that driver does is from startup, it calls a function called install multiple protocol interfaces, and it passes a struct to that function. Inside that struct, there are multiple fields. There are fields for evaluating whether a device is compatible with this driver, whether to start the driver on a certain device, but it also contains fields that are just numbers or pointers or something random. Once it's installed, the UEFI core just remembers that there is a driver, and then when now later on something like a PCI driver goes and finds that there is a PCI device, it creates a PCI object, and then asks every driver, whether it actually supports that PCI device, and that one then can say, yes, sure, that PCI device is actually the PCI device that I am the driver for, and the driver can then go in and say, sure, now it gets started, and then the driver goes and creates a block device inside the UEFI object space. Right. Using a call called FOSDEM multiple protocol interfaces, where you can basically create an object or attach protocols to an object. Protocols, again, are callbacks into something that you can find. You can find things like, please give me all devices in the system that support block device-like callbacks. And this thing basically implements one of those. But again, you can see that you have multiple callback function pointers and data structures. And again, you don't know which ones are where by definition. It's just part of the specification of what the particular protocol implements. Then your payload, the thing you're running on top of your UEFI, goes in and can, for example, find objects that implement block interfaces and call them. So Grub, for example, can go and say, please give me all block devices you have, which then means all the objects that have a block protocol attached to them, and then call a read function on those, which then means it can read data from the block device. Now, how do you put all of that into a virtual context and emulate things? And what are the problems when you're trying to emulate code like this? Well, for starters, the biggest issue is that different CPU architectures have different application binary interfaces, usually as the standard for UEFI. So the application binary interface defines things like the structural layouts and where things are, things like the endiness, which way around to print, to write characters into memory. So if you take a look at this structure of this particular block structure in memory, then on your x86 system, it will basically look like this. A little ending system is 64-bit, so everything is 64-bit aligned. And you have just a couple of pointers and a 64-bit number on top. Well, it turns out that on an AH64 system, it actually looks exactly the same. Because the API is compatible in this regard between the two architectures. If this was a 32-bit architecture, everything would fall apart. The pointers would be 32-bit long, everything would be differently aligned. But because those two architectures are so similar, the structure just happens to be identical. So there's another nifty corner case, which is padding. So different APIs, again, have different standards on how to pad things, how to make sure that a pointer, which is the thing you see down there, the reset function callback is a pointer, that a pointer actually starts on a natural boundary. And a pointer in a 64-bit case is 64-bit long, which means it needs to start on an 8-byte boundary. Which it does here, in this case on x86, because we basically take the 32-bit number, write it down to memory, and then leave 4 pieces of memory unallocated or unoccupied. And then it shows we need to write the pointer into the slot. Those 4 times. Well, it turns out ARM does it exactly the same way. So on AX64, that same API compatibility is essentially assured. It means, in a nutshell, if you had, imagine you had a CPU that could run ARM code and x86 code at the same time. Everything they keep in memory would look identical. They could basically pass pointers left and right without having issues. There are corner cases to that really work 100%, but at least for everything we care and we wrote about, that would work. We can basically, those two architectures, the APIs of those two architectures that are used on the UEFI, in UEFI are 100% compatible for integers. So that means that in theory, imagine we had an ARM graph running, calling into an x86 read function. Because the structures are the same, the ARM graph can actually find the pointer to the read function, because it knows exactly the offset that read function's pointer is. So it can call it. But what happens on call, really? I mean, what happens in the CPU when you're trying to call a function? Function calls are actually pretty simple. You have a function and pass arguments to it, and what happens is that you basically just take all those arguments, put them into registers. This again is defined in the API. And then you take the address you came from, put it in a stack, and you change the address you are at into the new address that you're trying to access, that you're trying to run from. That's all there is to a call. But imagine that this instruction that you're trying to execute now is an x86 instruction because we loaded an x86 option ROM into our ARM system. You saw earlier that the instruction sets are completely orthogonal, they're completely different. So you couldn't just execute that code, right? It wouldn't work. So we have to do something to actually get us into an emulator at that point. But how do we get into an emulator? We can't just go and change all the structure callbacks into something different because we don't even know which fields of the structure, which fields of the structures are pointers at which ones are data, because the structures can contain any random keys at any random point. It's not fully random. We could create a huge emulator that knows every single protocol there is in this world and knows all the structures for every single protocol there is in this world, and then tries to replace function pointers with function pointers that trap into the emulator, but that would be insanely hard. So basically Art's trick back then was, why don't we just use this amazing feature called no execute? So modern CPUs have a feature called NX, no execute, that basically allow you to, on certain regions in your memory space, say, well, yes, this region can be read and written, but as soon as somebody's trying to execute code from that region, just don't run this. Tell me about it. This is usually a security mechanism for user-based applications. Imagine you have an exploit that tries to put code onto your stack. This mechanism is used to protect the application from such an attack because basically the application can then say that my stack, I will never execute my stack, just mark my stack as no execute, so that if somebody tries to attack you through your stack attack, you get a set call instead of malicious code executed. But in this case, you can misuse that region and just say, well, every time we load x86 code, we just mark the region of the code that is x86 code as no execute, which gets us a trap. And on a trap, we can do whatever we want. And now we do know, oh wow, this application, this thing what is running, was trying to execute x86 code, and then we try to do something about it. So we can swap into our emulation state. We can just execute an emulator at this point that tries to then read that x86 instruction stream and make sense of it. But to do that, well, we were just calling a function, right? So what do these registers actually mean on the other end, which is x86? Well, it turns out x86 again has an API, which is slightly different from the x64 API for function callbacks, but it's convertible. So what you can do is you can basically take all the registers that are also stored in registers as function callbacks from the ARM side to the x86 side, in this case. Then there's a special thing on x86 where you can only fit 4 parameters into registers. So the fifth lives on the stack, which, well, you can just put it on the stack, that's fine. And then we also put in the return pointer, just fine, and execute the code in UEFI instead of QEMU, because we can now just simply execute x86 code. But imagine that x86 code is now trying to run ARM code, because it, for example, wants to allocate memory. And you can do the same thing again, actually, the same trick. So not exactly the same, but it's very similar trick. So our emulation code knows which regions are x86, because it registered them in the first place, right? It knew exactly where it put those x86 binary code pieces. So what it can do is, it can say, oh, well, this x86 code was trying to jump into an address that is outside of the scope I'm actually supposed to emulate. So it generates a trap internally where we can just move all of those pieces, basically do the API conversion backwards again, take all the registers from the x86 state, put them into ARM state, and emulate a function callback on the ARM side. What that gives you is you can basically have a fully chained mode of operation of calls. You can have ARM code, say, call into x86 code, say, the driver, call into core UEFI code, say, memory allocation. And the switch over between where we emulate and where we do not emulate, that one happens on a function level boundary. So you basically now have a system where every single function could potentially be either x86 or ARM code, and they both communicate with each other and they just live happily about it. Biggest question is, does it work? Yes, it does. So this is me. This is me in front of a monitor displaying a picture using a NVIDIA PCI graphics card on an AMD CIO system. So that firmware, and this is Graph, by the way, if you didn't recognize it. So this is in UEFI. So this is actually displaying something using, so this is ARM Graph displaying something using an x86 driver right off the graphics card. So why did we use TCG on that one? There's a couple of reasons why we use TCG. The biggest one for me, for starters, was C. There are a couple of alternatives, like Box, for example, which is C++ code. But if you look at EDK2, which is the core implementation and representation for UEFI. Oh, right. Andrea was just saying that I should explain what TCG is, which I completely concur with, since it's not quite obvious. TCG is the emulation engine inside of QEMU. So QEMU has used to have a different emulation engine, and now, about 10 years ago, recently switched over to something called TCG, the tiny code generator. And so this is basically the emulation core of QEMU. So why did you use that part? Well, it's C code, which fits in really nicely with EDK2 because it also is plain C. If you were trying to put C++ code in, then you would suddenly have to start worrying about things like exception handling, which you have to fit into the C model somehow. So that gets complicated. TCG is very well isolated. It was originally written exactly for the purpose of taking an emulator into different projects. So this was originally based on the TCC project, which is a tiny code compiler. So this was used to be the backend for the tiny code compiler, which basically was able to compile Linux on boot within 4 seconds or so. So you could always compile your own kernel when you booted it if you want. And then there's another really big one that's basically most of the core code there, is LGPL. And now actually everything we use in this project is LGPL, which means that I'm not going to get into legal issues with GPL code running in an environment that basically is very close source friendly. I don't want to even remotely be involved in lawsuits of people complaining that their whatever drivers now need to be open source because the firmware can be considered a big general entity and the emulator is part of it, and because that's GPL is tainting everything. And TCG supports x86-64. It sounds trivial, but if you look around and you're searching for emulators for instruction sets, you find a dozen at least emulators for 32-bit x86. But good luck finding one for 64-bit x86. TCG is really 1 out of 3. So how do they use this thing? I guess everybody of you now has their ARM systems at home, with PCI Express, of course. And you want to put your NVIDIA graphics cards in there and just try it out. Or maybe you just run a virtual machine and emulate your ARM system to emulate x86 codes. Which you can do. There's a GitHub repository, it's also the Mark's GitHub site called x86 emulator package. And that's a very easy thing to basically compile an OVMF build. OVMF is the firmware used inside of QEMU if you're running the virtual QEMU machine. If you want to go to a QEMU machine inside of QEMU, on an x86 virtual machine. If you're running on a random host and you're running an ARM virtual machine, then this is basically the binary you're running while you're running that virtual machine. The description is also on the GitHub site, so it's just but you can see it's actually not hard. We just do the same thing you would do if you were building your firmware manually, but you also just say, please also refer to this module over there and everything else is matched. It just works how it works. I guess you want to see how it works for real, not just the picture of me standing in front of the screen and the fake. So the demo is going to be exactly what I explained. I'm going to run an ARM virtual machine on my x86 notebook running an option ROM, an x86 option ROM that's passed in using an Intel Ether Express network. Make sense? Yeah. So for starters, we're going to run the emulator with the normal vanilla version without the emulator. So this is basically just going to run a virtual machine, a stock virtual machine with a stock EDK2 firmware that is exactly the way you would find it in a normal distribution. So you can see that it boots up, and it basically shows you that it didn't find anything. You can look at PCI, and you can see that it found an E1000E, E1000E adapter. So it found the PCI point, and if you look at -A-L, you can see that there is no network device at all whatsoever, because the normal OVMF, the normal firmware you're running does not contain a driver for the E1000E code. Because that usually in a normal environment comes with the card. So if we run the same thing again with a firmware that's compiled with the x86 emulator included, you see one major difference in that the firmware actually goes and tries to boot off of DHCP and then loads stuff from there, which is an ARM grub. This is exactly the case I was explaining. So this is an ARM grub running on an ARM system, because this is an ARM virtual machine, but the whole network driver, everything that was loading from the network, everything it's doing there, is going through an x86 driver accessing the network card. The emulated network card, but still it's network. And then you can just use it and it works. Basically, it feels like a normal driver that you don't even realize that it's x86 code. It's just exactly as if that firmware driver was actually written in ARM code. And speed-wise, you don't even see the difference. I'm not going to go through installation now, but for questions.
So you spoke about instructions and data, but do you have also to take care of that sort of interruptions also?
The question is, we're taking care of instructions and data, and whether we need to take care of interruptions. What do you mean by interruptions? Interrupts?
Yes, interrupts. Maybe some network data generations of interrupts will ask some behavior from the UEFI.
Okay. So yes, the question is basically related to interrupts. How do interrupts get handled? Interrupts are always abstracted away in EDK2 and in the UEFI framework anyways, because your device driver does not have direct access to the network, it doesn't even know necessarily what interrupt controller you have, so you always basically just give it pointers and callbacks into what you want to get called when there's an interrupt arriving. And there's nothing keeping you from running the emulator inside an internal context. So you have to think about it, but the conclusion basically is you don't have to do anything about it because it just works. Yeah. Okay, so two questions. First question is easy to answer. This works during boot time, so basically when you boot up your system, what do you need to do to make... That was the question. Sorry. I just got a silence and I repeat the question. It was a question. So the question is, this works during runtime, during boot time, so basically when your system boots up, but does it also work during runtime? So when your Linux operating system with the blue line, when your Linux operating system is running and threw away most of the UEFI code, UEFI can actually preserve some pieces there and make them available to Linux. The answer is very simple. Yes, it falls apart. Let's defer that to later and first answer those two questions so that I'm terrible at stacking if I get multiple things on top. So yes, it falls apart because we basically removed the x86 emulator while from the whole context. So you would now have ARM code calling into x86 code for real. The good news is it never happens because there is basically no support in Linux at least for anything that really does runtime services that an optional move provide. So it happens by accident. It happens to work by accident, but it is an accident. I do agree. Linux. So the question is, Linux never calls into an optional in a normal environment, in normal circumstances, and under normal circumstances, Linux never calls into optionals in the first place. The only thing that could happen is that the driver registers a special thing for runtime, a special runtime service that Linux could call into. And that could happen, but I'm not aware of any Linux drivers that actually do that. Art might know something. Good point. So Arm just said that the emulator, so we have code that basically the way the runtime driver would get initialized is that you have another PE binary that gets loaded, and that gets marked as a runtime driver. And we refuse to tag for runtime drivers, so it wouldn't even get loaded. We'll just refuse to load that driver. It could mean that things would potentially not work in the way you expect them to work. I do agree. Was that related to it? They can? Oh, okay. So
it's just for that easy.
So yes, I think the answer is there's another special case for network drivers that for the recording. There's another special case for network drivers that are not allowed to register runtime services anyways because they have that runtime driver thing. For the U-boot question, the problem is that a lot of, in general, this would be trivial support for U-boot. But in U-boot, we only implement interfaces that are facing user applications. We are implementing very few interfaces that an actual device driver would use. So for iPix, we might make it work. But for your NVIDIA network card that only uses some PI random callbacks, which we don't even remotely use. So yes, we could, but does it make sense? I don't think so. Actually, you know what? You get a microphone. it works. The button doesn't do anything. If you can make it work, just stick to that. There's a button that doesn't light up. But let's do it in my plan.
Oh. Okay, so one thing I'd like to add, which is kind of throwable to what you but it's your remote driver, which is the only driver we have on our Linux, proprietary system. The remote driver is quite likely to work better if the optional one has run first. So if the remote driver sees their hardware, might find it in a state that's different from the processor.
What was that question? Oh, okay. More questions?
It seems to me like the problem you have solved was supposed to be solved by EBC, the UEFI bicycle. Whatever happened to it? I thought it was
Oh, he was expecting that. It's in the backup.
The question is, all of this should have been solved by EBC. What happened? If you like to write their courses, EBC is a great option. It doesn't even have a compiler as far as I know anymore. It's essentially abandoned. EBC doesn't exist anymore really in the field. There's no optionals shipping with EBC, and the problem we're trying to solve is that you have existing devices you want to run, and these existing devices will definitely have x86 optionals, and basically zero chance of having EBC optionals. So you could either work on with vendors to have an x86 option ROM and an ARM option ROM placed there, so that it would run native ARM code if it finds a native ARM system, which already works. Or you could work with them to convert into a completely weird zombie-ish platform that nobody really cares about, which sounds to me like a bad idea. So it's just value.
I can add a little bit to that, Alex, since I'm Brian Orpington before UEFI and stuff. We had this discussion in the UEFI forum a couple of years ago, and it talked about maybe someone who write an EBC interpreter for ARM. Because for years there was an interpreter for either Q64 to EBC, because it was a problem that Intel kind of created, so we wrote the code and made it popular. So we went probably that list an Intel compiler for an Intel problem. Not too popular at all for some reason. I don't know why. But at the end of the day, when they looked at it, most of the vendors really wanted to run native code. If they were going to strap a driver to hardware, they would just ask the hardware vendor to give you a native ARM driver. And so you're solving this small corner case problem with servers where there's not an ecosystem for it. There wasn't really anybody who would have EBC, right? And then have the problem of having a carrier, you have to carry around two option ROMs anyway, one for EBC and one for x86 64. Well, if you're going to carry some anyway, just make it on 64 and x86 64.
So the increase in the size of the firmware is large. The increase in the size of the firmware because you entered you added the emulator to the firmware.
If the firmware is about 10 megabytes and you add 300K, it's not really.
That's the number I wanted to. I'm not including my
I don't remember, to be honest. It was certainly negligible compared to the overall size.
I'm just interested in the number.
I did do the benchmarks when I started the board, but I don't remember the exact numbers. And just speak it out. So this question is how long before this gets merged upstream? There are basically two things blocking this. The biggest thing is that it's using a framework to trap the PE loader. So we need to basically, when a binary gets loaded, we need to say, well, I know that this is a binary that's not meant for your architecture, but please load it anyways and tell me about it, and then I will fix things up for you. And that interface is not in core EDK2, and getting this in is, from all I hear, very painful, because you first have to write about 200 pages of Word documents to actually get things proposed. That's what I heard. But if you can get a shorter route, I'm more than happy to do that. Example. If I can just submit a patch and it's in.
It's less complicated than you said, a little more complicated. Unfortunately, you have a lot of your
Here sounds great. So time's up. Answer is apparently soon. Thank you.